Hello world, this is Craig. So yesterday was kind of a big day. I got my EPROM programmer running, and so I was able to transfer my monitor program, which I have been using this little add-on card that I made that has this 2732 in it. So I was able to burn all the EPROMs that go in my two ROM cards and run off the ROM cards for the first time. So that was a pretty exciting day. It was a little bit of moving things around because I had assembled this for certain memory locations and for everything to fit in this 2732. So I had to basically keep my original monitor program in this, and then in empty space above that, I brought in parts of the binaries for the individual ROMs and programmed the ROMs out of the top of that, and then I had to switch this out a couple of times to be able to finish all 10 EPROMs. But at any rate, I got everything programmed, got it in, and fired it up. I did come across, as I mentioned in my video yesterday, I was having trouble with my EPROM programmer, and so I wrote in my confidence test a extra little routine that allowed me to individually turn on the two multivibrators that we talked about in yesterday's video, and also it allowed me to output bits to the port, and then I simply went around with the oscilloscope and found out which bit was not being toggled, and traced that back to, or which bit wasn't having the proper pattern during the programming, and traced that back to a chip that where it had to be failing, and pop that chip out and put it in my little programmer here, tested it, and sure enough, it had a bad gate. So as an aside, if you are looking at one of these, this is the XC ECU or XG ECU or whatever, however they want that pronounced. These little programmers, I don't use it so much for programming EPROMs for a couple of reasons. One, it only goes up to 18 volts, I think, and a lot of my 2732s take 21 volts. It also has a dickens of a time opening a Intel hex file that is spread across various memory locations. So if you have some of it assembled at, say, starting at 0, and then you have more of it that you want to assemble up at 2000 hex, it can't open that file properly, and so I have other programmers that can handle the more unusual Intel hex files better than this guy. But for doing things with some things with pals and gals, and also for just checking gates in chips, boy, you can't beat this thing. You just pop it in and put in the identifier for the chip and ask it whether it is good or not, and it told me I had a bad gate in that. Fixed that gate, or just swap that chip out, and the programmer took right off, and then I was able to program everything yesterday like I mentioned. When I was porting the code over the monitor 80, that's the first one I did. First I did the monitor 80, I ported that over, and then I started porting the monitor 8 over. Well, I was looking at the monitor 80 code, and this is the programming portion of it, and as you can see, it's pretty sparse with comments. It's really hard to tell what's going on in here. But the key thing down here is to look at when they output to the programming port. So here's the out 026. That's where they're turning the multivibrator on. And it's port 26 for the 8080. It's port 13 for the 8008. And then they exclusively OR it. So they flip that bit, and then they output right to that port again. So you can see they are just doing a very, very brief toggle of that programmer. And if you work your way through the code, you'll see that they're basically setting up a delay loop, a counter, and then they trigger the programmer. And this counter, depending on what they preload that counter with, is how they either get their overall 15 millisecond or 150 millisecond delay. And so they're doing the entire thing in software. Well, they're doing the duty cycle in software, and they're always only using the 15 millisecond timer, and they're doing the duty cycle delay then by just doing a countdown loop. So it was a bit confusing when I was looking at the monitor 80 code, and then I started the monitor 8 code, I realized, well, hey, wait, compared to the Monitor 80, the Monitor 8's got all the documentation. So you can tell you can see which one came first. They said, well, there's no use bother to document this as much in the Monitor 80 because we've already documented it in the Monitor 8. So I should have looked at this a lot earlier, but I didn't look at it until I was porting it over, at which point I already had the Monitor 80 done. So now you can see what they're doing. It's quite obvious here, and it's kind of interesting. When they ask you to put in either the A or the N, basically what they're doing is they're taking that as an ASCII value. The A corresponds with the 1702A, obviously, but the N is kind of an arbitrary letter. But I always thought it stood for normal or something. I think that's what the instructions say. It stands for normal. But basically, the N was just chosen because it gives you a value. Its ASCII value is correct for the different duty cycles. You can see that if you input an A, it converts that to a 5 after it does some rotating and masking. And if you input an N, that gives you a 71, which is about 57 in decimal. So it's about 10 times bigger. So you can see that the difference between our 2% duty cycle and our 20% duty cycle, depending on what letter you put in. So you can put in any value you want for the duty cycle because you just give it an ASCII value. It does a couple of left rotates on that, and then it uses that as the counter for the countdown. And in the earlier documentation, I think instead of an N, the value for the 1702 was an L. So they updated that to change that duty cycle a little bit. And then you can see if you go down here, their timer, you can see E still has a timing constant. So they're counting down E 15 millisecond or 160 millisecond. This is where they're actually doing the duty cycle delay time. And right up here, you can say they set up for the 15 millisecond timer, pulse the generator, hit it once, giving 1 3 millisecond pulse. So this once I saw this, I saw what they were doing, and then the fact is they're not using the 150 millisecond timer at all. They're only using the 15 millisecond timer, and they're just doing all the rest in software. There's really no downside to doing that. It's not like they're going to be using the microprocessor for something else. They're not generating an interrupt. It doesn't have a timer or a clock on it. So they're not doing an interrupt where they're coming back and programming and multitasking and doing something else in the meantime. And what this does is it allows them to speed up the programming because without doing this, they have to assume a certain number of program cycles, and then they would check to see if the data matches and then do more programming cycles. With this, they're basically doing one program cycle and then checking if the data matches, and then doing one program cycle and checking if the data matches. So they will catch much sooner when the data actually matches, rather than doing this in blocks of 10, for example. And that really will cut down because they do the 4 times over programming. And if you were doing them in blocks of 10 and the first block of 10 was successful, but you're going to do a 4-time over programming, so you're going to program another 40 times. But let's say that it was successful on the very first try. So you did one program cycle and it was successful. Then they're only going to do 4 more, so you did a total of 5. And you can see that appreciably speeds up the programming time. So that's probably why they decided to do it this way. And I've done that before, where you design a beautiful piece of hardware to take care of a bunch of stuff, and then you just wind up short-circuiting all that in software and skipping a lot of the things that you had built into the hardware. And if we look at the waveforms on that, we can see we're getting the same result. Here is their little spike. Right here is their little spike. It's 14 microseconds, where they are just outputting to that port, flipping it, and then outputting it again. And then that starts our standard programming sequence. They then wait the appropriate amount of time, in this case 18 milliseconds, and they do it again. So this is, and we can see the top parts here are for the longer timer. And those are all stable. They're not doing anything. They're doing everything with the shorter timer. So this is what it looks like if we do the short timer. We can set that up for the long timer. We can see that all the signals that would be triggering the long timer multi-vibrator are all stationary. They're not doing anything. We see the little pulse that they give the 15 millisecond multi-vibrator and trip it. And then they do a 200 millisecond delay to get the proper duty cycle. So that's just what we were seeing in the software. As I said, we can put in any value we want. So for example, if we put in a G Let's see what we get. So here's a G. We're getting a 100 millisecond delay between the programs, between the pulses. Okay, well, that's all I had for today. I was pretty excited. I got this thing up and running on its own ROM memory cards using the 1702As, and that was a pretty big step. And wanted to share that, and then also just give some insight to what they were doing in the programming. And if you were trying to do some debugging, maybe don't expect exactly what the document says. The best thing to do is write a little diagnostic or a confidence test that you can individually control the pins and control which multivibrator is turned on. That's all I had for today's video. Thanks for watching, and if you have any questions, let me know. Talk with you later. Bye-bye.